Today's topic is Magneto-Mechanical Coupling. So of course, we will go into the governing equations for mechanics and magnetics, and then detail the coupling mechanism between both PDEs, and finally discuss some application issues and also implementation issues regarding the finite element method. So let's start with a quick example. Imagine you want to compute this lift magnet. So you have a magnetic core here in gray, a coil around to induce a magnetic flux. Then it is clear that the flux in this core will depend on the size of the air gap here denoted with x0, and here in the equation the current position. If this lifted piece is actually moving, the air gap will become smaller, and the magnetic flux and thereby the magnetic force will change. So it's of course important to take into account mechanical deformations, in this case of the lifting piece. It's not the deformation but the motion mostly into account for these coupled problems. And of course this poses a few challenges. First, we have the challenges of the sub-problems, because they can be often nonlinear. For magnetics, we know due to the material properties. For mechanics, it can also be material properties. It could be other nonlinear effects like contact or geometric nonlinearities. The next challenge is that we actually need to know the magnetic forces on the mechanical structures. So this is one of the coupling mechanisms. Additionally, in the magnetic sub-problems, the motional electromotive force must be considered. So this is the force that arises when a conducting body is moving in a magnetic field. Another challenge is mechanical deformations change the magnetic domain. So this needs to be taken into account in the magnetic sub-problem. And furthermore, then we have mesh deformations, because the mechanic structure deforms. However, in the air domain, we typically don't have any mesh deformations. So these must be handled in some way. And most of these challenges are actually addressed in Manfred Kaltenbacher's book, which we closely follow in this lecture. So if you want to have any detail, you can find them in the reference given. So let's start with mechanics. Our governing equation is the balance of momentum, where the unknown field is the mechanical displacement field denoted U in our mechanical domain omega m. The loading in terms of the volume force density on the right hand side should be known. And of course, we can also have boundary tractions as boundary conditions for the mechanical PDE. And to close the equation system here, our stress tensor sigma is unknown. However, we can use the constitutive relation to relate the stress tensor sigma to the strain tensor S, and the strain tensor is typically related to the unknown displacement field by differential operators. They can be linear or they can be nonlinear in the case of geometric nonlinearity. Similarly, of course, the constitutive relation can be linear in the simplest case, Hooke's law, or it can be nonlinear too. So this is our mechanics problem. So let's look at the other problem, which is the magnetics problem. And here we will restrict ourselves to the eddy current problem. And this we see we can formulate in terms of the magnetic vector potential A. So we have impressed current densities on the right hand side. We have the time derivative of the magnetic vector potential. So these are the eddy current terms. We know that the magnetic flux density is related to the magnetic vector potential via the curl. We know our material properties, the magnetic relectivity. This can in general be nonlinear, and the eddy current terms. I've already mentioned the last term in the equation actually considers the effect of a moving electrically conductive body in a magnetic field. So V denotes the velocity of this motion. So usually the eddy current problem, as it's written here, is formulated in an Eulerian description. But we have seen that actually we want to take into account the mechanical deformation. So we want to actually formulate the magnetic problem in a Lagrangian frame. So let's look at how we can formulate the time derivative when we consider the deformed geometry as a reference. So let's look at the total change of the magnetic vector potential, or any vector quantity, in fact, with respect to time. So we write the difference quotient. So we have to take the difference of the field A at the new position and the new time minus A at the original position at the original time, and we divide by delta t. And now we can do a Taylor expansion of the first term, so of the A at the new position and in new time. And if we do this, of course, we have to take into account all the derivatives. Make note that the x is actually, so the new location x is actually a function of time. So here the first partial derivative is clear with respect to time. That's one dependent variable, but A is also dependent on x. And that's why, and since x is also dependent on time, that's why these partial derivatives of x with respect to t come here in the mixed term, and we have neglected higher order terms. And if we now closely look at what is here, the x with respect derivative of x with respect to time and y and z and so forth, we see that this can actually be written in compact vector notation by the velocity vector, since the derivative of the coordinate of the material point with respect to time is actually the velocity of this material point. So if we now take the expression for delta t to 0, we obtain the material derivative. And so this is the common expression for the material derivative. We have the partial derivative with respect to time. So this is the expression we had in our Eulerian formulation, and additionally a convective term. So if we now take this and use it in the formulation of the eddy current problem in the Lagrangian definition, we proceed as follows. So the first step is to insert the material derivative, the last equation, in the original eddy current problem. The second step is to actually use the vector identity for the last term in the eddy current problem. So this term was gamma times Vx curl of A. And there's a vector identity that tells you that you can write the same expression equivalently as this A gradient of V in A minus V in the gradient. So this is a new operator, V in the nabla operator applied to A. Note that the nabla A denotes an operator that is only operating on A, so V is unaffected by this operator. And if we rewrite this motional EMF term with this vector identity, we see that the last term is actually the same term that we had when we replace the time derivative with the material derivative. And so that's the final expression we end up with. We have now the correct form of the eddy current problem in the Lagrangian frame of reference. So this last term here is important. Note that this last term is not always important. In fact, it's always zero if you have a two-dimensional case. And this is the case because in this case, in the 2D case, the magnetic vector potential is always perpendicular to the velocity vector because it always points out of the computational plane. So usually that's the z direction. So AZ is the only component of A, and the velocity, of course, is only in the computational plane. So V and A are orthogonal in the 2D case. So that's when you can neglect this term. But in 3D in general, you need this convective term. So now we have both our PDEs ready and we are ready to actually consider the coupling. And the coupling is on the one hand side due to the electromagnetic force. And whenever you have a mechanical body in a magnetic field, there is a volume force density arising due to the magnetic field. And the volume force density can be written in the following form. JXB, so J is the current density, B is the magnetic flux density, minus 1/2 H in H times the gradient of mu. So we recognize two terms here. So the first term is the Lorentz force, this describes forces due to currents flowing within a magnetic field. So if you have a conductor here, you have a current flowing here through here, J, and it's placed in a magnetic field B. They're already perpendicular, and you see the cross product will give you the magnetic force. And similarly, or not similarly, but the second component is the pole force. And that actually, when you look at the expression, arises whenever the magnetic permeability is inhomogeneous. Otherwise, you don't have a gradient of mu, then it's zero, and these terms become zero. So typically this arises at interfaces, for example, at an iron-air interface, and that's why it's called pole force. Also recognize that the magnetic force depends in a non-linear manner on the magnetic field. You always have products of magnetic field quantities here. So JXB and A in H in H. These are both quadratic dependencies on the magnetic field. And due to this, we can't directly formulate a direct coupling, but we have to usually use an iterative coupling scheme for solving both PDEs. Let's look a little bit how we could derive this electromagnetic force. And one answer is to use the principle of virtual work. So what does this principle say? It tells us that the variation of the magnetic energy must equal the total virtual work done by the magnetic force density. So the total magnetic energy variation is delta capital Wm. So if we integrate the energy density over the volume, we get the total energy. And similarly here, for the mechanic equivalent, we compute the virtual work by the virtual displacement in the force density. So delta R denotes our virtual displacement. And this can actually be used to derive the expression for the electromagnetic force given before. I'll just highlight the main steps for this derivation. So first you start from the magnetic energy density for linear materials. Then you assume isotropic material with the permeability. Do the variation on the magnetic energy density expression. And then there's one trick. You come up with one term that is B in delta B over mu. And it turns out that this can actually be written as the delta R in JXB. So this is how you come up with the Lorentz force term, and the other term amounts to the pole force. So evaluating the pole force is not quite is not that easy. So let's discuss this a little bit. We have to evaluate the expression A in H gradient mu. And the problem is that we have to evaluate this over the material interface. And at the material interface, the mu is typically discontinuous. So evaluating this gradient is difficult. And one solution to this difficulty is to actually transform the volume force density to a surface force density. So let's consider such a part of the interface. So we have permeability 1 on the left side and permeability mu2 on the other side. And let's consider such a cylindrical domain in the direction of the normal vector. So if we integrate over this, we start integrating from mu1 and end up at mu2. The length is h, so from R1 to R2. The cross-sectional area is delta gamma, and the total volume is then delta omega. So delta gamma times h is delta omega. So we consider this infinitesimal cylinder. The axis is, as I said, in the normal direction, and we want to compute the total force on the cylinder by integrating over the volume. So the total force is then the force density integrated over the volume, and the integral over the volume we can actually compute by the cross-sectional surface times the integral in radial direction. And finally, we have inserted the expression for the pole force with our gradient mu here. So now the third step is to consider the normal component only. And we can do this actually if we consider that the mu1 and mu2 are spatially constant over the cross-sectional area. This is actually also a requirement to do this integration in this form. So then if we only want to have the normal component, of course, we compute delta F in N. So this is our normal component. So we have to multiply the in N also into our expression. So we can put it in here. And then we can see a nice relation we can use here, because the change in mu is actually the gradient evaluated in normal direction. So that's the only gradient by our assumption, mu1 and mu2 spatially constant times dr. So this we can actually use to replace interchange the integration. So we don't integrate over dr, but we integrate over d mu. So we have nicely removed our gradient by this trick. And then we can also let our dr go to 0. The next trick we need is actually to decompose the integrand, so our h, into tangential and normal components. And we can just do this by the normal vector and an arbitrary tangent, or the tangential vector of the field. So HT is the tangential component, and we have to sum up with the normal component Hn. So we can do the same with B, of course, too. And then we can rewrite the expression H in H. And then, of course, always consider that a lot of terms will be zero, since the normal component and the tangential component are always orthogonal. So if we do this, split in normal and tangential component, and also replace via the material law the Hn by the Bn over mu, then we come up with this simple expression of B squared n over mu squared plus Ht squared. This is written as a scalar since the inner product of the same vector is of course the magnitude squared simply. Okay, and then we can finally evaluate our integral. If we assume zero surface currents, we know that Bn and Ht are actually continuous over the interface. So that's why we split up in this manner, that we can use this continuity property over the interface. And if we do this, we can simply pull out the Bn and the Ht from the integrals. Which is nice, because then we can obtain a nice closed form solution for this integral. And finally, we can compute the surface traction term by just dividing the surface force we got by the surface area, so the cross-sectional area, and let the area go to zero. We obtain the expression for the pole force density in normal direction. Note that the pole force always points from the region with the larger magnetic permeability to the region with the smaller magnetic permeability. You can see this by noting down the direction of the normal vector, which also defines where the domain 2 and the domain 1 is. So you have to factor that in. Okay, so we have an expression for our pole force. However, as usual, there's another way to compute the pole force. So one way would be to evaluate this expression over the surface, and another way is to again use the principle of virtual work. And for this alternative method, we consider all the air elements around our moving body. So a layer of air elements around our around our interface. And then we consider that the virtual displacement leads to deformation of the surrounding finite elements. So we can use the virtual work principle here written again to compute the volume force density. So if we insert here to build the integral, we have to sum over all the elements. So this is the complete integral. And here we have inserted the general expression for the magnetic energy. If we now consider we have a linear material in the air domain, we can switch to the more simple expression we had before. So 1/2 B in H, and we have already expressed the H via B over mu 0. And now we need to do the variation. And if we do this, we can compute the derivatives. Just take note that you only not only B has to be varied, but also the omega So this is why we get these two terms here. And so now this was the complete expression. And if we only want to get the nodal force, which is what we actually apply in the finite element sense, then as a force acting at the finite element node I, we only have to consider the elements that are adjacent to this node I. So the sum is getting much smaller, and that gives us the nodal force contribution for this single node. Also take note that the force direction has actually three components, so we have to do this dr variation in all three spatial directions. So finally, we can look at how the semi-discrete finite element formulation looks like. So we have already applied the Galerkin procedure and obtained our system matrices here in the mechanical domain, written as the mass matrix, as a stiffness matrix that can in general depend on the displacement vector or vector of nodal displacement if the problem is nonlinear. There can also be a damping matrix inside. And on the right hand side, we have the mechanical forcing vector, which depends on the magnetic degrees of freedom by the magnetic force. In turn, the magnetic problem, again, we have mass and stiffness matrices that depend now on the mechanical deformations due to the change in the geometry. So this is why this U dependence comes in, and of course the magnetic problem may be nonlinear itself, and also the right hand side of the magnetic problem is configuration dependent. So to sum up, both problems are nonlinear and have nonlinear dependencies, and it's useful to actually conduct an iterative coupling in each time step. So first, we usually solve the magnetic problem with the initial configuration, compute a forcing for the mechanical problem, solve for the new displacements, and iterate on. So let's look at the picture of the iterative coupling scheme. So start with the magnetic field until the nonlinear field is converged, and then we compute the magnetic forces, apply them to the mechanical field. Again, it might be a nonlinear mechanical problem, so we have to iterate here until we have convergence, and then we obtain displacements which are fed into the magnetic problem to alter the geometry, and we have to recompute the magnetic problem. And of course, this iteration loop we have to do in each time step should we have a transient time-dependent problem. Of course, we can't iterate forever, so we need a useful stopping criterion. And what is useful is to take actually a relative norm, for example, on the displacement field. So we take, we also always consider the current time step, so n+1, and we take the difference between current iteration k+1 and last iteration, and we norm this by the current or the last iteration. Doesn't really matter what you take here for the norm. It is also useful to take the relative norm of the coupling quantity, for example, the magnetic force. That can also be a useful stopping criterion. Usually, if you take relative norms, the stopping criterion is not that strict, so 10 to the power of -3 is already rather good in this case. Note also that you can actually combine several stopping criterion. So you can either say, okay, I stop iteration if one of them is met, or if all of them are met. This depends a bit on the application, what is useful. So if you want to use this in practice, you can, of course, use OpenCFS. We can do nonlinear eddy current problems. You can compute the magnetic forces, so Lorentz and pole forces. You can compute nonlinear mechanics problems. We have iterative coupling schemes using various tolerance criterion between the two PDEs. We can account for mechanical deformations in the magnetic problem by using an updated Lagrangian formulation. And hopefully soon we can again use mesh smoothing in order to get rid of problems in the air domain. To show a little bit how this mesh smoothing technique is working and why we need it, let's consider again our lifting magnet. So just consider this lifted piece is actually displaced more than the size of the first element rho here in the air domain. Then we have, of course, very distorted elements and even negative Jacobians, which will be impossible to integrate. With these severe mesh deformations that will quickly arise in the air domain, we have numerical problems. So one solution would be, of course, to solve the mechanical problem in the whole domain, because then every node has a displacement degree of freedom, and this problem doesn't arise so quickly. However, this is a bit of an overhead for the mechanical problem, and you also create numerical problems if you have domains like air with a very small artificial stiffness. So a nicer solution is actually to solve a pseudo-mechanical problem in the air domain. So consider you solve the mechanic problem here in our mechanical domain, so the blue domain that can actually displace, and you obtain displacements here on the interface line. And now you solve a new mechanical problem in this pseudo-mechanical domain, so the air domain here encompassed by this dashed line. And here you apply the true mechanical displacements as Dirichlet boundary conditions. And by this you obtain a nice displacement field in the air domain, and hopefully your Jacobians and element distortions are not too severe. So here's a picture of this actually, of how this actually looks like. So here the gap is in the original configuration, and then it gets smaller and smaller, and you see that the mesh smoothing seems to work rather nicely in the air domain, and we don't have too distorted elements. Yeah, this was already all about Magneto-Mechanical Coupling. The reference here is Manfred Kaltenbacher's book. And of course, there are questions for learning reinforcements.